Radiation in Medicine. Basic Radiation Physics. By Assistant Professor of Medical Physics, Dr. Al-Arif.
Source of radiation. Radiation is a form of invisible energy either emitted as waves or particles and propagated through space. Radiation generally produced when fast particles interact with material or atoms goes to decay. A large contribution of radiation on Earth comes from the sun, solar energy, or from radioactive isotopes found under the ground, terrestrial elements. We refer to the natural radiation around us from different sources as a background radiation, which is varied from point to point on Earth.
Radiation units. The International Commission of Radiological Units and Measurements, ICRU, recommended a special units for radiation measurements. The becquerel, BQ, which is a unit used to describes the activity of radioactive elements, where 1 becquerel equal to 1 disintegration per second. The old unit for the activity is the Curie, C, where 1 C equal to 3.7 by 10 to the power of minus 10 becquerel. The Gray, G, is a unit used to describes the radiation dose in the SI unit system. The main types of radiation frequently used in medicine are alpha particles, beta particles, gamma and X-rays.
Isotopes. Isotopes are two or more elements having same number of protons but different in neutrons number are called isotopes, which are unstable elements decays by emitting energy in a form of radiation. Deuterium and tritium are two isotopes for the hydrogen atom. In addition of having one proton, they have 1 and 2 neutrons in the nucleus respectively as in the figure. Alpha particles decay. As in the figure, radium nucleus is a massive nucleus of 226 nucleons, including 88 protons and 138 neutrons. It decays by emitting an alpha particle composed of 2 protons and 2 neutrons. The radium nucleus turns into radon-222 nucleus, itself radioactive, containing 2 protons and 2 neutrons less. The disintegration releases 4.6 million electron volts of energy. Beta particle decay. As in the figure, in beta decay, the atomic mass not change, since the one of the neutrons from the carbon-14 nucleus converted into a proton, and a fast electron is ejected, beta particle. The remaining nucleus contains 7 protons and 7 neutrons, which is a nitrogen nucleus. Gamma decay. Some atoms contain excess energy and become excited. It emits energy in a form of electromagnetic radiation, gamma ray, by rotation or vibration to go to more stable state, as you can see from the figure.
Rate of decay. Radioactive decay is the process by which a nucleus expels mass or energy in order to become in more stable state. We are interested in the types of radiation emitted when atoms decay, and in how frequently the atom emits this radiation. Some radioactive substances have a very high rate of decay, while others have a very low decay rate. To differentiate different radioactive substances, we look to their decay rate. No two radioactive materials having same rate of decay. There are 5 common types of radiation decay. 1. Alpha decay. 2. Beta decay, either. Positron emission. Electron capture. 3. Gamma emission.
Laws of radioactive decay. As in the equation, the number of radioactive nuclei, n, available after time, t, is equal to the original number, n0, of nuclei multiplied by the exponential formula to the power of minus lambda by the time, t, where lambda is the decay constant. The above equation can be rewritten in terms of activity of the material by substitute the activity A instead of n and the original activity A sub 0 instead n sub 0 in the above equation. The half-life, t, is defined as the time required to disintegrate half number of radioactive atoms in the sample. Then if we substitute A by A sub 0 over 2 and the time, t, by the half-life time, t, in the previous activity equation, then we get the following equation. The half-life time, t, equal to natural log of 2 divided by the decay constant, lambda. You can see from the figure that the activity of the sample decreases exponentially with time. And the first half-life time correspond to 50% activity, and the second half-life time correspond to 25% activity. Ionization versus excitation. Ionization is the removal of one of the orbital electrons due to the transfer of the energy to the atom. Electromagnetic or particulate radiations capable of producing number of ion pairs by interaction with matter are called ionizing radiation. Ionizing radiation can damage and alter biological molecules, thereby causing cells death, or mutation. Excitation happen when the energy transferred to the atoms not enough to produce ionization. In excitation some of the electrons move to higher energy state and return back after the removal of the energy absorbed. Ionizing radiation penetration power. The figure shows that alpha particles can be stopped by a piece of paper. Beta particle can penetrate the paper but not a piece of wood. X-ray and gamma rays can penetrate the paper, the wood but not a wall from lead. Directly ionizing radiations, charged particles that have enough kinetic energy to produce large number of ionization by direct interaction with matter are called directly ionizing radiations. Example alpha particles. Beta particles. Proton, P, particles. Indirectly ionizing radiation are uncharged particles or electromagnetic wave that can only produce little number of ionizing by direct interaction with the matter. Example, neutrons. Gamma and X-rays. The exposure, X, is the ratio of delta Q by delta M, where delta Q is the sum of all electrical charges produced in the medium of mass delta M. The unit of exposure in the SI system is the Röntgen, R. Absorbed dose, D, is the ratio of delta E by delta M, where delta E is the energy deposited by ionizing radiation in the medium of mass delta M. The unit of absorbed dose in the SI system is the Gray, G, where 1 Gray equal 1 joule per kilogram.